It is in our best interest to keep measurement variation under strict control. Our efforts, however, have mixed levels of success. Calibration is one way we can control measurement variation. Standards and definitions on how to quantify parameters have existed for many hundreds of years. Standardization allows companies across the globe to use a single established manner of quantification. This is one of the reasons why programs like ISO exist and are embraced. How else can one organization quickly and effectively understand the operations of another company? Measurement tools degrade over time. Calibration allows us to compare a measurement standard or instrument of known accuracy with another standard in an attempt to correlate as well as adjust and monitor the instrument's performance. Calibration programs are not far-reaching, though, and can only help us eliminate measurement variation. The precision of measurement can best be improved through the correction of the causes of variation in the measurement process. As mentioned earlier, measurement error can have many sources. Operator variation occurs when the operator of a measuring instrument encounters variation utilizing the same equipment on the same standards. Operator-to-operator variation is when two operators of a measuring instrument see variation utilizing the same equipment on the same standards. Equipment variation lies within the instrument. There are many sources of equipment variation, including wear out, damage, and misuse. Material variation can be due to the normal dispersion evident in processing materials or through destructive testing. Procedural variation results when there are multiple methods used to measure the part. Software variation can occur if there is an error in the code used to measure the part based on any number of input factors. Laboratory-to-laboratory variation is much like operator-to-operator variation. When procedures differ from lab to lab, variation can result. Standardized testing helps to eliminate these sources of variation. The calibration interval is based on stability, purpose, and degree of usage. We have already discussed stability. An instrument that is shown to drift over time must have more frequent calibration scheduled over an instrument that is more static. The purpose of the measurement instrument is also an important consideration. If the instrument is used to measure a parameter that can be tied to the potential for physical harm, safety, or customer satisfaction, then a more frequent calibration interval would be warranted. Instruments tied to measurements with minimal exposure to risk can be checked far less frequently. The environment where the instrument is used can also be of interest. Instruments used in hostile environments will likely degrade more easily over those maintained in controlled environments. Remember that intervals can always be adjusted. Within many quality management systems, we are expected to collect, study, analyze, and adjust calibration frequencies as needed. This is one part of the overarching aim to continuous improvement. When starting a calibration program on an instrument, start out by planning to check more frequently. If you discover that this is overkill, adjust accordingly. Make sure to maintain thorough and traceable records. When devising a method for calibration, resist the urge to reinvent the wheel. Organizations such as the American Society for Testing and Materials have many established test methods that describe the test conditions, equipment, procedures, and so forth to be followed. Other organizations like the National Institute of Standards and Technology produce secondary standards that include documented certifications for accuracy. An example would be gauge blocks or calibration pins.